Okay, let's go ahead and get back together. Keep going. So in the last class, we covered the idea of equivalent capacitances. Here we're going to talk about equivalent inductances. The equations are not the same, but you may recognize these equations as well. Now I'm not going to go through the process of deriving these. I think that the process I went to derive the capacitance ones were interesting. They show you how to calculate those types of circuits. But inductors, I mean, it's just KVL and KCL again and again and again. And what you come to find out with is, well, you have the idea if multiple inductances are present in a system, we want to represent them as one inductance. Why? Because that allows us to figure out current flows, voltage flows, power, all of those things that are coming out of a power source. Because remember, the power source either provides a voltage or current, but it does not know how much power it is providing. It actually looks forward into the system and says, here's how much power I have to provide before it does anything. Okay? So it depends on the circuit how much power it provides. So in order to figure out how much power it's providing, we need to know what the circuit general behavior is. So having an equivalent inductance would allow us to do that. Okay? So if we had a system of inductors in parallel, what's going to happen to the current going into those inductors? Are they all going to have the same current? Are they going to have different current? What's going on there? Do these all have the same current? If I say L1 equals 2 henries, L2 equals 4 henries, and L3 equals 8 henries, do they all have the same current? What? Probably not. Because, I mean, you have a current coming into this node, and then it has the possibility of going down 3 different branches. You're probably not going to have the same current going through all 3 of them. Okay? So not having the same current going through all 3 of them means what you're dealing with is all of them have to have the same voltage, right? So here, VL1 equals VL2 equals VL3. Well, if we replace VL1, VL2, VL3 with their equivalent relationships, that means that L1 L1 dt equals L2 di L2 dt equals L3 di L3 dt. Okay? And since L1 is not equal to L2 is not equal to L3, it means that your current changes are also going to be different. So we are expecting there to be different currents through each of those branches. Okay, just to generate the same voltage. So with them not having the same current, what we see is, okay, anytime we add another component in parallel, we're actually going to reduce the amount of current that every individual component sees. So the way that this ends up behaving is in parallel the equivalent inductance, LEQ, is equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus dot dot dot. In series, this is IS, L1, L2, L3. Are each of these going to have the same currents? What do you think, Caden? What do you think, Caden? Just gonna look at him. Yeah, they're all gonna have the same currents. And why is that? Because they're in series. If you look at the KCL equations, current coming into that node is equal to the current coming out of that node. There's only one coming in, there's only one coming out. And for each one of these, current coming in equals current coming out. Current going through L2 is going to equal current going through L3, because the current going into node 3 is equal to the current going out of node 3. KCL has to be true. Okay? So all of these are going to have the same currents. So in series, IS is equal to IL1 is equal to IL2 is equal to IL3. Okay, so what this means is that if we were to take the derivative of all of them, what that means is that I can say that DIS dt is equal to DIL1 dt equals DIL2 dt is equal to DIL3 dt. If these are equivalent, then their derivatives are also equivalent. We can say that. If those are equivalent, their integrals are also equivalent. Well, most of the time, assuming that they start at the same initial conditions. Integrals get a little weird, but we know that their derivatives are equivalent. If they are equivalent, their derivatives are equivalent. Okay? And then if we just plug this back into the equation, we know, well, if we multiply each of these by L1, L2, L3, all this means that V L1 over L1 equals VL2 over L2 equals VL3 over L3. I'm just using this equation. Just using this equation. Okay? Just plug that equation in multiple times. We know that that condition is true. And we can then prove this. In series, if they all have the same current, this relationship is true. Okay? Well, this relationship is also true for resistors in series. So it turns out, in series, L equivalent is equal to L1 plus L2 plus L3. Okay, this is the same equation as we saw. Was this the same equation we saw for capacitances in parallel or series? Parallel, and was this the same one as we saw for resistances in parallel or series? That's a parallel resistance. So inductance has the same equation as resistance. It's nothing new. Turns out when you do the same math formulas all the time, you eventually get the same formulas all the time. And that's really a lot of what this class is. It's just the same formulas over and over again. It's kind of easy to teach. That's one of the reasons why I've memorized most of the formulas. You just say them all the time. The same thing. Everything is a derivation of KCL and KVL, mixed with individual relationships between voltage and current of components. That's really it. That's all that this course boils down to this point. Okay, any questions about this? All right, let's get funky, which is exactly what you'd expect to hear from a guy in a green suit. I know, right? I'm gonna write my own theme music. I'm gonna have everybody call me Doctor. Hey, Doctor. That's terrible. I just wrote an ugly word on the board. My apologies for my profanity. All right, we now have a non-constant DC source. What does that mean? Well, DC means that it doesn't oscillate. AC sources oscillate usually at a frequency of 60 hertz. DC sources are constant. They do not oscillate. They do not have harmonic functions. However, I am giving you a non-constant DC source, which means that the voltage that's coming out of this source, which, I mean, it could be that we hooked this up to a Norton equivalent circuit. And this is the current that we're getting out of that equivalent circuit. Doesn't mean that we exactly have a power supply here. It just means that this is the system that we're facing. This is the amount of power that's coming out, okay? We know that this is what the relationship is, okay? The question is, can we figure out what the voltage is for each of these three components? And we'll go ahead and say L1 is equal to 1 Henry, L2 is equal to 2 Henries, and L3 is equal to 3 Henries. Can we figure out what the voltage is across each one of them? Now, if I asked you what the voltage is across each number, that's kind of a trick question because that voltage changes. Like, what is the voltage? 7. Yes, it is 7 at some point. I mean, it's true, but you gotta plot it because the voltage is constantly changing. This is no longer a constant value. We are now looking at a function of time. So how do we figure something gross out like this? Well, let's start out by plotting IS with time. What does that look like? At 0, what is the value of IS? It's 0. Plug in 0 for t, you get 0. Okay, at 1 second, what is the value of IS? -3. So that will doot. -3. At 2 seconds, what is the value of IS? Yeah. Nice work. Okay. At 3 seconds, it goes back to -3. 4 seconds, it's back to 0. Okay. So the function looks like this. Now we're going to ignore everything that happened before t equals 0, just because we have to pick an arbitrary t equals 0 time. But that's what our IS looks like. It's a parabola. And it turns out it's actually centered around t equals 2, but it's whatever. So that's what IS looks like. Awesome. Now what? Well, the beauty of this system is that they're all in series. What is true about components in series? Yeah, you're getting ahead of me though. But yes, you are right. What's true about components in series is that components in series all have the same current. Have to, according to KCL. If they're in series, they have the same current. Okay, and because they're in series, then yes, your equation is right. You just took one step ahead of me. So all components are in series. So if we do KCL, then what that shows is that IS equals IL1 equals IL2 equals IL3. That's nice because now I don't actually need to know what the voltage is on every single one of them. I just know that that equation is true. Okay? Because the currents are equal on all of them. The derivatives of the currents are equal on all of them. Okay? This isn't just a single value. This is something that exists in perpetuity. This exists at all times t. These values have to be equal because of KCL, which means their derivatives also have to be equal, which means the second derivatives always still have to be equal, which means the 10th derivatives always also have to be equal. If they're all equal, then the derivatives of those functions are also equal. Okay? Now this is nice for us because now that we know that these derivatives are equal, well, we also know that this is equal to, so we know that according to our relationship that I gave you at the beginning of class, dIL dt is equal to VL1 over L1. It's just a rearranging of the relationship between voltage and current in an inductor. Okay? That's where we're at now. But we also know that this is equal to this, which is the source current. So dIS dt is equal to VL1 over L1. What is the derivative of IS? Two t minus 4. Okay, which means that VL1 is equal to L1 times 2t minus 4. Which means that VL2 is equal to L2 times 2t minus 4, which means that VL3 is equal to L3 times 2t minus 4. Now, what I want you to note here, the functions for VL1, VL2, VL3, they're just scalar differences of each other. Right? All they are just change L1, L2, L3. Done. They all have the same driving function. 2t minus 4 is present in all of them. You can pull it out of every single one of them. Why is that important? The voltages all change in relationship to each other. All of the changes that the voltages experience, they're all very close to each other. It's not something where one changes and the other one's like, well, I'm going to decide to be 3t minus 5 this time. No, it doesn't do that. Okay? They all have the 2t minus 4 because they all have the same driving time function. And that driving time function is based off of the original power source. Okay? For constant voltage sources, we saw the same relationship. Everything was a scalar of each other based on resistances, based on capacitances. Okay? That is going to change a little bit when we get into first order and second order systems. But everything has a very close relationship with everything else in the circuit. Everything does. Any component in a circuit has a relationship with everything else in the circuit. Especially for very simple power circuits. Okay, not nearly as true when you get into high order systems where part of the circuit is oscillating and part of it isn't. Then it gets a little weird. But for simple power circuits like this, all of the components have a relationship with each other. All of them have the same driving time function. So if we go to plot these, VL1, T, what is this going to look like? At t equals 0, what is the value of this function? Yep. Because L1 is 1, yes. Okay. At 1 second, what's the value of this function? Guess I should write out the actual. Those are T's, not pluses. I feel like I'm drawing a fish hook. What's the value at 2 seconds for VL1? Oh, yeah, dang, I forgot 1 second. So it forms a line that goes like this, okay? If we were to plot out now VL2 with t, what is the value of the function t equals 0? It's -8. What's the value of the function at 2 seconds? I said 2 seconds. Gotcha. It's 0. What's the value of the function of VL3 at t equals 0? -12. And what about at 2 seconds? It's 0 again. They're all just scalars of each other. Okay? So if we want to then take all of that information and plot out what is Vs, how do we do that? Do we have any equations that we can use to figure out what Vs is? I put on the board KCl. Yeah, we can put up KVL, which, again, you're getting ahead of me, man. Slow down a little bit. Dang it. Let me teach. Gosh. If we write up the equation for KVL, there is exactly one loop for the system. Okay? If we have exactly one loop for the system, it means that the sum of the voltages in that loop have to sum to 0. If the sum of the voltages in the loop sum to 0, then what that means is that Vs is equal to VL1 plus VL2 plus VL3. Vs equals VL1, VL2, VL3 added together. All right, so graphically, what does that mean? Huh? It is linear. We can add all of these together. If we just add the values at t equals 0 and t equals 2, it's going to be a line. So it's going to start out, let's see, -4 plus -8 plus -12 starts out at -24. So that's awesome. And then it goes to t equals 2, it goes to 0. And then that's our line. At 4 seconds, it's back at 24 volts. And then it just keeps increasing forever. That's what our source voltage looks like. You'll also notice this function has the exact same appearance as these functions. Because it's these three added together, because it's L1 plus L2 plus L3, because that's the equivalent inductance, multiplied by the time function of the current. That is the equation for Vs. That's why equivalent inductances help. Okay? All right, let's play around with this a little bit just because we can. What in the actual heck is that? Now this time, we have a negative current. What does a negative current mean? It means the electrons, at the start, the electrons are flowing this way through the system. Okay? What does this negative voltage mean? It means that in reality, because this is driving voltage, we actually have a switch on the voltage here where this is the positive terminal of the battery, this is the negative terminal of the battery, and each of these are supplying voltages to the battery. It's sucking voltage out of them. It's actually reducing their energy. Okay? To a point where at t equals 2 seconds, it stops reducing their energy, Now, the current is still flowing this way through the system, but at t equals 2 seconds, this now starts putting energy into the components. It's no longer pulling energy out, it is now pushing energy into the components, which is why they have a positive voltage. But you still have a negative current. Electronic systems are whack. I think that's a great conclusion. That's really what it comes down to. You can have weird behaviors out of systems where you have a negative current and a positive voltage, where the current is flowing backwards through your system, but each of these components are being charged. Or rather, undischarged, if you want to call it that way. Yeah, no, they're being charged. So that's fun. What happens if I were to give you the exact same time function, and instead of having this be in series, this was in parallel? All of the components are going to be the same. The equations are going to be the same. The method of solving is going to be the same. We're just going to do it for the components in parallel now. L1, L2, L3. Same system, different configuration. Now, are these components in series or parallel? But I did say it was in parallel, so I hope that I drew it correctly. Because they're in parallel, their voltages are all equal. Okay, so we know that if we do KVL, our VS is equal to our VL1, is equal to our VL2. If I stand right here and talk, I can hear my voice vibrating off the bottom of that metal thing. Equals VL3. It's very distracting. We know that relationship is true. Unlike the last one where things went easily and it was like, oh, let's take a derivative. Whee! Oh, we don't quite get to do that. Because we know these are the same, the currents are going to be different through each of these components. Okay? We know, well, first I'm going to write out KCL. We'll take that relationship, we'll leave it for now. We have two nodes in our system, node 1, node 2. We can go ahead and ground this one just for funsies. According to KCL, what do we know is true? What is the equation that we get from KCL? I think that was true for a different example. KCL is just the I in equals I out. Yeah. Oh, was that what you were saying? We'll go with that. I in equals I out. Okay, so at node 1, what is your input to node 1? What is the current that's flowing into node 1? Again, you just keep getting ahead of me, man. Dang it. But you were right, but yeah, wait for me, man. It's IS. If you answer the next one with the formula, I'm leaving. What is the current flowing out of node 1? You're trying to come up with a formula, aren't you? I gave you a challenge. The formula all boils down to 2t minus 4, smarty pants. But what is the current flowing out of node 1? Yes, but we have 3 of them, so it's going to be IL1 plus IL2 plus IL3. Okay, and if we do KCL at node 2, we'll get the exact same equation. So we don't really need to write KCL at node 2. So doing KVL, we have what? 1, 2, 3 different loops. We get those equations. Using KCL, we have 2 equations, but both of them are identical. That's what we have to work off of. The only other equations that we have are the individual relationships between voltage and current. Okay? So this KVL is equation set 1. KCL is equation set 2. And then we know that VL1 equals L1 IL1 over, DIL1 dt. VL2 equals L2 DIL2 dt. And then VL3 equals L3 DIL3 dt. This is our equation set 3. Fun fact. Every problem we've solved, we've used all 3 of these equation sets. Every one. It didn't matter if it was last class, didn't matter if it was resistances, didn't matter if it was capacitances. It doesn't matter for this whole class. We will always use these same 3 equation sets. I gave you these equations on day 2 of class because we use them every friggin' problem. Because this is how we understand the circuit. Every single circuit is subject to KVL problems. There's always going to be a circuit. Hence the name circuit. Okay? Which means there has to be a loop. Every single circuit is going to have nodes. Hence, KCL becomes relevant. Every single circuit is going to have components. And each of those components is going to have a relationship between voltage and current. Every single problem we have solved has used those 3 equation sets. Nothing changes just because we're using inductors, except for the fact that now we have to use, integrals. So I guess something has changed. But it's just the same thing over again. Same thing. And when we get into first order systems, we have the same thing over again. Although then we have to do really complex derivatives and partial differential equations, and it's not nearly as much fun. I hope you all enjoyed resistance while you could. What? You're a pleasure to have in class, Trace. Real stand-up guy. What is with you and the deadpan humor? How can you do that with a straight face? I have to laugh at my own jokes, and here you are, like, knocking them dead, just no expression. You ever thought about doing stand-up?
Never.
Okay. Okay, back to this. So we have these 3 equation sets. One of these equations contains all voltages. One of these equations contains all currents. One of these sets of equations contains the relationship between voltage and currents. You see what we're doing there? Amazing. That's why we use the same set of equations in every single problem. Is because one of them is voltages, that's KVL. One of them is currents, that's KCL. That's what the C stands for. And then the last one is the relationship between the two. Okay? Those are all equations we need to solve this problem. Nothing else has changed. So I am going to take all of these equations and we're going to form an equation soup and we're going to pull out some Vs value. Okay, and then we'll compare it to our original one. And then we'll move on at the end of class and talk about parasitic effects. And then we will play with Raspberry Pis next class. Pies. And then things get really sucky in class. Yeah, next week. Your reading assignment for next week, anybody who's looked ahead? Yeah. That's the part where I'm actually planning on carrying my camera around the room because I will fill up an entire board with one problem. Yeah. Yes. Yes. It's coming. Winter is coming. All right, so let's make an equation soup out of these. We know these are all equal to each other, which is great, because that'll allow us to eventually solve for Vs. We know these exist, which is great. We're going to go ahead and plug these, equation set number 3, into equation set number 1. So what we end up with is Vs is equal to VL1 is equal to VL2 is equal to VL3. Okay? So what we know now is Vs is equal to L1 DIL1 dt equals L2 DIL2 dt equals L3 DIL3 dt. Okay. Well, that's gross. What do we do now? We have these weird derivative things in there. Keep looking at me weird. Yeah, what? I throw an elbow at it, but I don't want to like, bam, right through the wall. I'm like, why is there a hole in the board? I had an equation look at me weird. That would not go over well with facilities. I have broken a desk once because I was doing a handstand in class. Yep. It was high school. I then cowered in a corner. Yeah. And since then, I've been hesitant about doing handstands in class. But now we have all this. You know what? I'm going to go ahead and drop out Vs out of this because we don't really need it anymore. I mean, we could drop out most of these. But I'm going to just drop out Vs because what I'm about to do is something I'm going to regret. It'll haunt me in my nightmares tonight. We have to assume some initial conditions. Okay? For the last one, we assumed that the, blah. Now, the initial condition that we have to assume is this. This is the initial condition we have to assume. Okay. So we're going to have to take the integrals of each of these. L1 DIL1 dt dt equals the integral of L2 DIL2 dt dt equals integral of L3 DIL3 dt dt. Now you'll notice that the dt's cancel out in all of these because we're just integrating with time. And what you end up with is L1 I L1 plus C1 equals L2 I L2 plus C2 plus L3, oops, sorry, not plus, that's equals, L3 I L3 plus C3. Where because we did an indefinite integral, we don't know what C1, C2, and C3 are. Sucks. Dang it, math. Thought we were besties. You're gonna do me dirty, jerk. But we also know this relationship is true. IS is equal to all of them added together. And that has to be true for all times t. Okay? So we can go ahead and solve each one of these in terms of, say, IL1. Okay? So we're just going to solve in terms of IL1. So that we can plug into here so that we can have one variable and one known constant. So here, breaking this equation up and from 3 back into 2, we have L1 IL1 plus C1 equals L2 IL2 plus C2. That means IL2 is equal to L1 IL1 plus C1 divided by L2 minus C2. Fun, fun, fun. 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 Oh, the C2 actually goes up top. My bad. Okay, if we do the same thing for IL3, we get the same thing. IL3 is equal to L1 IL1 plus C1 minus C3 divided by L3. Well, that's gross. Why are all these C1s and C3s in here? It's so disgusting. No, that's terrible. Worst day ever. Gross. Okay, so what we get with this is if we plug this into equation set 2, which is a derivation of the mixture between equation set 3 and 1, that's what this is, IS is equal to IL1 plus this funky thing plus this funky thing plus L1 IL1 plus C1 minus C2 over L2 plus L1 IL1 plus C1 minus C3 over L3. Well, that's disgusting. I'm going to go ahead and pull all of my constants out and put it at one side. Okay? I don't know how that sounded on camera, but it probably sounded awful. Oops. Did everybody show up? Oh. Remember being cool. No, nobody cares about my life anymore. Oh, dang, I just said that on YouTube. Forgot to shut off my mic. Okay. I'm going to go ahead and pull all of our constants out to the right side and keep all my IL1s over here. Just rearrange this equation. So I got IL1 plus L1 IL1, so L1 over L2 IL1 plus L1 over L3 IL1. You know, this would have been a lot easier if I just would have done an equivalent inductance. Good job, Kale. Nice. Nice. plus, and then all my constants, I have C1 minus C2 over L2 plus C1 minus C3 over L3, okay? And I know that equals to IS. Now, IS is equal to T squared minus 4T, which is a problem. Because if we compare time functions from one side to another, what we're going to end up with is, we know IL1 is going to be some function of time. So if we just rewrite that, IS is equal to some function of time, IL1, plus, and you know what? I'm going to define C4 as that. Okay, and then this IL1 also happens to be, I guess I should write out the full equation. IS is equal to 1 plus L1 over L2 plus L1 over L3 times IS. And then we add C4, and where C4 is just an amalgamation of all of our constants, okay? Trying to solve this without using equivalent inductance, which is what I did for the last problem with the equivalent capacitance. I don't know, there's no one right way to solve a problem. I just happen to be doing it the hard way. Okay, the issue with this, yeah. This thing? Yeah, it's a T. I'm sorry. This is an IS. No, sorry. This is an IL1 as a function of time, because we know it's going to change. Okay, the issue is when we write out IS here, IS is equal to T squared minus 4T is equal to 1 plus L1 over L2 plus L1 over L3 times IL1, which we know is a function of time, plus C4. Our time values have to be identical on both sides. Since we do not have any constants on this side of the equation, we can't have any constants on this side of the equation. Right? You can't add plus 1 to x squared and ever equal an equation where it's x squared. You know, it's just x squared. Okay, you can't have ax squared equals bx squared plus 1. This is impossible. Because you always have that weird freaky plus 1 out here. What you end up with is the plus 1 has to go away. And then you find out that A equals B. This is kind of the same situation here. You can't have a weird constant here. C4 has to equal 0. And you know what? That's going to be true for everything. Turns out C1, C3, and C4 all have to equal the same number. And in order for us to figure that out, we'll have to plug it in, make sure that the time values are correct. But we now know C1 equals C2 equals C3. They may equal 0, they may not. We don't know yet. But we do know that that equation goes away here because it has to, because there is no constant in IS. If there was a constant in IS, C4 would have to be something. And then we could solve for C4, and then we could solve for IS, and then we're in a good place. And then everybody has a happy day, and we're all just having sunshine, lollipops, that kind of a thing. Okay? So, here's where we're at. Awesome. Now, if we would have done equivalent inductances, this would have been a lot simpler. We should have done that. I did not do that. But now we have this time function, we know this function, and we know this scalar. Okay? If we were to go back and write out the functions for IL2 and IL3, we would find that t squared minus 4t is equal to 1 plus L2 over L1 plus L2 over L3, I L2 of t, and also t squared minus 4t is equal to 1 plus L3 over L1 plus L3 over L2, I L3 as a function of time. It's just plug and chug and doing exactly what we've already done. Okay? Now the nice thing is, all three of these have to add together to equal, well, yeah. All three of these have to add together to equal one of these. But this is the relationship by which we scale IL1. So really what we end up with is, what is the value of 1 plus L1 over L2 plus L1 over L3? It's 1 plus 1/2 plus 1/3. That's 1.5, isn't it? Okay, and then down here, this is 1 plus 2 plus 2/3. 2 plus 2/3 is equal to 3 2/3, which is equal to 11/3. And then this last one is 1 plus 3 plus 3/2, which is equal to
9/3.
Are you sure it's not 11/2? Wait, is this 9/3? That can't be 1. 1 plus 1/2 plus 1/3 equals 1.5. Has to. Has to. Oh, man. Dang it, head maths. Questioning myself now. Okay, this is equal to 3 2/3, which is 11/3. Okay, and then this one is equal to 3, it's 5.5, which is equal to 11/2. Okay, so I1 is equal to 2/3 IS. I2 is equal to 3/11 IS, and I3 is equal to 2/11 IS. That doesn't make any sense. Shouldn't that be 12ths? 5/11.
I was talking about the first one.
The first one is a 3.
Yeah.
Oh. What is it? You said 9 halves? 9? It's not 9. It goes into 6. This is 2/6 plus 3/6, which is 5/6, which is 11/6. Right. So then this is 6 11ths. There we go. Okay. Thank you, by the way, for pointing out that I was wrong. Because I was very wrong. This is our new relationship. And now if we just scale IS, we get those values exactly. Now once again, we're dealing with the same thing. These are scaled values of our original forcing function, which is this. If we go ahead and plot this, well, this one, it's going to look like this. And then the other one's going to look like this. And then the third one is going to look like this, okay? See what I did there? I just do the same thing 3 times. You just scale that. This one is 6/11. This one is 3/11, and this one is 2/11. That's it. Just scale the whole thing. They're all scalars of the original function. All of them add to equal the same parabola if you sum them all together. But now what is Vs? Well, if we take the derivative of this, multiply it by L, we'll get the same voltage for every one of these. So we really only need to calculate the voltage for one of them. So if we calculate the voltage for one of them, VL1 is equal to L1 dIL1 dt. We take the derivative of 6/11 times IS equals L1 times d dt of 6/11 times inside function t squared minus 4t. This is equal to L1 times 6/11 times the derivative of t squared minus 4t, which is equal to 6/11, that's 111, times L1 times 2t minus 4. Okay, so if you go ahead and plot this out, VL1 equals Vs equals VL2 equals VL3. With time, you get a function that looks like that. And it starts at 6/11 times -4. It becomes equal at 0. At t equals 2 seconds, it crosses 0. But this is 24/11. It's gross. Okay. Is that voltage relationship similar to the one before it? Very much so. It's the same shape, different magnitude, has the same overall behavior. It's just a different number. Why is that? Well, it's because we're dealing with inductances here. Inductances are going to behave similarly. Even if they're put in parallel, even if they're put in series, they're going to have the same relationship between current and voltage. And here, the shape of the current graph is identical for both of them. Even though they're in series versus parallel, the shape of the current graph is still the same, which means the shape of your voltage graph will also be the same. All right, I'm going to take a 10-minute break, and we're going to have 5 minutes of class left over. So let's do that. I'll come back at 10:25, and I will jam everything else in a